In this example, we're going to evaluate integral of square root of 4 minus 9x squared dx. This integral is a good candidate for trigonometric substitution because of the expression that we have inside the square root. Well, besides the fact that neither basic substitution rule or integration by parts would help us here in this case. Okay, so what about this expression inside the square root? What makes it so special? Its structure. So here we can see that we have a constant minus, well, another constant, right, coefficient x squared. And when we use trigonometric substitution, our goal is to see what kind of basic trigonometric identity this expression might resemble. Now, we usually choose from those three identities. Let's see which one is the closest to this expression based on the structure. Now, first of all, one of the identities, notice how it has plus sign. That one we're not going to consider since we have a minus sign. We have difference. Now we have two choices here, the first one or the third one. Well, with expressions involving minus sign, we want to be careful and note the order. So the order in which we have terms here are the following. First comes the constant and then x squared, well, with the coefficient in this case. It means that identity that we choose should follow that pattern. So first it should be a constant and then minus function squared. And based on that, it means that we have to choose the first identity, right? We have to go with the first identity. Next, our goal is to somehow to do appropriate substitution so we can end up with expression 1 minus sine squared of theta inside the square root. Because after we do that, we're going to change 1 minus sine squared of theta with simply cosine squared of theta. So it's going from difference to just one term, right? That's kind of good, the first benefit of that. And the second is that square of that cosine is going to cancel the square root. That's another good thing that we're going to obtain. Let's think. So obviously, where I have x here, well, somewhere over here is going to be sine, right? And I'll start, it's not going to be exactly the substitution we're going to do, but it's definitely going to involve sine, so I'm going to write it down. Next, I have to know that while the overall structure, when I look at this expression kind of like from far away, it resembles the pattern of this left-hand side of the identity, but as I look closer, well, I see that I don't have 1, right? I don't have 1 here, and now I also have this extra coefficient, so I have to deal with those constants. Now, this first constant, the standalone constant, usually the way to turn it into 1 is by factoring. Let's say if I could factor out 4 out of this expression, then I will have 1 in this place, right? But the problem is that I cannot factor out 4 at this time since I don't have 9 and I don't have 4. So I need to create 4 here and get rid of 9. How do I do that? Well, to create 4, what I can do, I can put 2 in front of sine. Because now as I square 2 sine, and I will have to square it, right? Because this is just x, so all that has to be squared. Then it's going to become 4 sine squared, and that will give me 4 in front of this term. But how about 9? How do I get rid of 9? Well, I can get rid of 9 if it's not just 2, but 2 over 3. That's if I use this kind of coefficient. Let me make a note. So x is going to be 2 over 3 sine theta. And now as I square that, once I plug it in, 2/3 becomes 4 over 9. Now this 9 in the denominator is going to cancel 9 that I have here as the coefficient, and then 4 will stay, and that's going to be the common factor that I will factor out along with this 4, and I will obtain the left-hand side of my identity. So let's try that. So from here, I'll have integral of, I'm not going to be skipping any steps, so I'll just write them all. So in other words, I have 4 minus 9 times. Now instead of x, I am plugging in 2/3 sine of theta. And since x is squared originally, that expression has to be squared. Well, what it means that it's squared is that now in the next step, as I simplify, I'll have to apply square to 2/3 which means that to square both 2 and 3, and then I will apply square to sine, like that. And well, actually, we have to now think about what to replace dx with, differential dx, right? Everything has to be in terms of theta as soon as we perform substitution. So, well, but dx is pretty easy to obtain from here, right? If x is 2/3 sine of theta, then dx is 2/3 cosine theta d theta, right? So dx I will replace with 2/3 cosine theta d theta. Okay, so I'm writing it here. You know what, I'm going to put 2/3, so here 2/3 cosine theta d theta, but 2/3 I can put in the front of the integral, right? 2/3 cosine theta d theta. I have to be careful here that cosine is outside of the square root, right? Let's continue. Now we have to simplify. So once you perform the original substitution, simplify as much as you can. And through this simplification, square root has to go. As I said, I'm not skipping any steps, so that's what I have inside the square root right now. 4 minus 9 times, that becomes 4/9 sine squared theta, and then cosine theta d theta. Next, that's 4 minus, okay, here it is, the simplification. 9 and 9 will cancel, and I have 4 minus 4 sine squared theta times cosine theta d theta. Next, inside the square root, this is all happening inside the square root, I can factor out 4, right? And that, again, that's all happening inside. Inside the square root, I'm factoring out 4, so it becomes 1 minus sine squared of theta. Okay, here it is. That's the identity I was going towards, remember? Remember how we decided we're going to use 1 minus sine squared of theta equals cosine squared of theta? Well, here it is. We obtained it. We obtained the left-hand side, which will be replaced by the right-hand side of that identity in the next step. Times cosine theta d theta. So that's 2/3 square root of, integral square root of 4. 1 minus sine squared of theta, that's cosine squared of theta. This whole thing I'm replacing with cosine squared of theta. Cosine theta d theta. And that's where a square root will go away, right? So we finally can get rid of the square root. 2/3 integral square root of 4 is 2, and then square root of cosine squared is just cosine theta. So that's the result of the square root. Now next to it I have another cosine theta d theta. Great. And that's what I will need to evaluate now. So that 2 I will combine with a coefficient or with the constant in the front. So it's 4/3 integral, and that's cosine squared of theta d theta. So we just performed the second step, which was simplification. You can totally skip some of those steps, but overall that's simplification. So you simplify as much as you can. So once you simplify it, you want to look at the resulting integral and think about how to evaluate that. So because of the trigonometric substitution, you will always end up with trigonometric integral, right? And there are different kinds, and there are different approaches to evaluate them. Sometimes you're going to get just a basic integral, but in this case we ended up with integral of cosine squared. Well, there is no basic formula for that, so we have to be creative. We have to refresh how to evaluate this kind of integral. So when we have a trigonometric interval that involves 1 or 2 functions, but all of the functions raised to the even powers, we would need to use half angle identity. So what is that identity? It goes like this. So cosine squared of theta equals 1/2 times 1 plus cosine of 2 theta. I need another parenthesis, okay. That's identity. It's you know, it's one of the versions of half angle identity, but it's a convenient version in this case. So I'm going to be replacing cosine squared with this. That 1/2 in front, I'm going to combine with 4/3. So that's 4/3 times 1/2 and 1 plus cosine of 2 theta d theta. Okay, and then I can easily evaluate. So first of all, number in front is 2/3, right? I can divide out to 2/3, and that's the result of integration. So integral of 1 is just theta, plus an integral of cosine of 2 theta is 1/2 sine of 2 theta. Now, if you're not sure how to deal quickly with 2 theta, it's just the basic substitution rule. So you can let u be equal to theta and go from there, but the only thing that you're going to get extra in this case is the coefficient 1/2 plus c. So that's the result. Now, are we done? Not quite yet, because we have everything in terms of theta, and we need to return to the original variable of integration, which is x. How do we do that? We have to look at our original substitution and use that to express whatever we have here, which is theta and sine of 2 theta in terms of x. Let's go back to our original substitution and think about it. Okay, so here it is. So from here, I can rewrite it and say that sine of theta is, okay, so I'm trying to get it by itself. It means that I have to multiply by 3/2 on each side, right? So it's 3 over 2x, right? Or I can also write 3x over 2, like that. What do I need to express in terms of x? Going back real quick, going back to here. I need to express, first of all, theta in terms of x. Well, if it's simply theta that I need to express in terms of x, then I can get it from here right away. So if sine of theta is 3x over 2, what's going to be theta? Well, then theta is going to be inverse sine function, sine inverse of 3x over 2, right? So we're kind of like switching places of theta and then 3x over 2. So here it's input, here's its output. If we want to switch those places, we have to obtain inverse function, right? Sine inverse. Okay, so theta will be sine inverse. I'm going to put that into my answer. Theta is, so 2 over 3, theta is sine inverse of 3x over 2, like that. Now, how do I deal with 1/2 sine of 2 theta? Keep in mind, that's very, very important, that sine of 2 theta, it's not just twice of sine theta, right? So there is no straightforward connection like that, like you would, I don't know, think in algebra maybe. So sine of 2 theta is not the same as twice of sine theta, something like that. It's just a very common thing to, common mistake to make. Theta itself and 2 theta are totally different angles. Well, I mean, 2 theta is double of theta, but generally they're different angles, right? So it means that their sine function values are different. And to connect sine of 2 theta with sine of theta, we need to use an identity. So this is what we need to do. Okay, I'm moving back. I'm moving back, and that's what I think about it, or make a note for myself. So sine of 2 theta, so we have to apply double angle identity. So what is sine of 2 theta? Sine of 2 theta is same as 2 sine theta cosine theta. So that is just an identity. That's another identity we're using here. Identity, right? So to find sine of 2 theta, we need to know, well, 2 is just a constant, right? Actually, that 2 is going to cancel 1/2 that's in front. But we need to take sine of theta and multiply it by cosine of theta. Well, good news that we already have sine of theta. Already have, right? That's our original substitution. Or we just, got it from the original substitution. But cosine of theta, we need to find. How are we going to find cosine of theta? Well, let's go back to our substitution. So sine of theta is, I'm rewriting it, 3x over 2. That's what I just said. We already have sine of theta, right? We're going to plug it in later. But how do we find cosine? So to find cosine, we're going to set up this right triangle. We're going to denote angle theta. And we're going to also label sides. Which sides can we label? Well, knowing that sine of theta is 3x over 2 and knowing that sine is defined as opposite side to hypotenuse, this tells us that we need to label side that's opposite of angle theta, which is right here, this side, this leg, as 3x, and we need to label hypotenuse as as 2. Hypotenuse is 2, right? Opposite side, hypotenuse. Now, what is cosine? Remember, we need to find cosine of theta. Cosine of theta is adjacent side to hypotenuse. Now, hypotenuse we already have. That's 2, so it's going to be over 2. But what is the adjacent side? It's over here. Adjacent side is found by taking square root. If you saw previous examples, then you looked at the steps behind it. I'm going to do a little bit quicker this time. So it's going to be square root of, take the hypotenuse, square that, and subtract the square of the other leg, minus 9x squared. Okay, so that's the adjacent side, 4 minus 9x squared. Let's put this all together. Let's try to put this all together. We have to be careful. So we have 1/2. I'm going to write this all. 1/2 from here times 2. Now I'm rewriting sine of 2 theta, expanding it using the formula, right? 2, that's this one, times sine of theta. Sine of theta is times 3x over 2. And then times cosine of theta. Cosine of theta, that is, we just found it, right? It's square root of 4 minus 9x squared over 2. Then I close the parentheses plus c. So I'm trying to see if I can make notes. So that's 2 from here, sine from here, and then cosine from that part of the formula. Let's simplify this. I can see that, let's see, those 2's will cancel, and we have what? I'm going to be multiplying, I think, let me distribute that coefficient. So 2/3 times, okay, 2/3 times sine inverse of 3x over 2, right? That's that part. And then as I multiply this constant from, as I distribute it and multiply it by 2/3 by 3/2, that will all cancel, right? So 2/3 and 3/2 are gone. It means that I only have plus, I only have that x times the square root, and then over, so that 2 stays over 2, right? And then plus c. So that's going to be the answer. Now, this example was a little bit tricky at the end. It's not going to be that tricky every time where you have to, apply this double angle formula. However, I'm warning you, if you have sine of 2 theta or cosine of 2 theta and you need to find that in terms of x, in terms of the original variable, you have to use the double angle identity to connect them like we just did here. So that's the example.